Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on into section 6.3, which introduces you guys to the concept of the kernel and the range of a linear transformation. The kernel and the range of a linear transformation are really important sort of properties of a linear transformation. So what we're going to be doing in this video is sort of taking a look at the definition of these two concepts, the kernel and the range. Then we're going to talk about basically a very important theorem that sort of relates the dimension of the kernel and the dimension of the range to the dimension of the domain of the linear transformation. We'll see that that theorem is actually an extension of an earlier theorem that we discussed, the rank nullity theorem. And then we'll look at some examples of understanding these new concepts of the kernel and range. So let's jump right into the definitions here. So we're going to be working with a linear transformation that is from one vector space V into another vector space W. So we know that it is a linear transformation. So the kernel of T is a subspace of the domain. It is written as KER of T, and it is the set of vectors in V that have the property that the transformation of that vector is the zero vector in the target space or in the codomain. So, in other words, the kernel of a transformation are all the vectors in the domain that get mapped to the zero vector in the codomain under that transformation. The range of T, which is a subspace of W, so it's a subspace of the target space or of the codomain, written as the RNG of T, is all the set of vectors W in that codomain such that there exists vectors in V so that T of V, the transformation of V, equals W. In other words, the range of T is every vector in the codomain that actually gets hit under this transformation. Now, you'll notice that it's very sort of strange here. I gave these definitions, and then we have down here proof. I mean, normally you don't have to prove definitions, but there is a actually little statement in here specifically that these are subspaces that we need to prove. Obviously, these are just sets that we've defined. They're definitely sets, but what we're going to prove is that each of these are actually subspaces. So let's go ahead and prove that, and then we'll look at a little visualization to help you guys understand what the kernel and range really is. So we'll start with the proof of this guy here. So we need to show that the kernel of T is a subspace of V. Now, certainly it is a subset of V because everything that is in the kernel is going to be inside of V. So what do we need to show that something is a subspace? Well, this stretches all the way back to what we discussed back in section 4.3. Remember, to show something is a subspace, you need to show that it is closed under addition and scalar multiplication. So let's let V1 and V2 be the elements of the kernel of T. What we first need to show is we need to show that V1 plus V2 is an element of the kernel of T. So how do we show that V1 plus V2 is an element of the kernel of T? Well, we need to show that V1 plus V2, when you apply T to it, is mapped to 0. So let's go ahead and check. So T of V1 plus V2. Since T is a linear transformation, we know that T distributes over that vector addition. So we can write this as T of V1 plus T of V2. T of V1, though, since V1 is in the kernel of T, must be the zero vector. So this must be the zero vector in W. And T of V2, well, V2 is in the kernel, so this guy must also be the zero vector in W. And again, when I write that subscript of W there, all that means is that we're talking about the zero vector, but in vector space W. All right, and obviously the zero vector plus the zero vector is equal to the zero vector. So that tells us V1 plus V2 is an element of the kernel of T. Check. Okay, so that shows that kernel of T is closed under vector addition. Now we need to do the same for scalar multiplication. So let's let V be an element of the kernel of T. Don't really need V1 and V2, and K a scalar. All right. What we need to show then is we need to show that KV is an element of the kernel of T. So let's go ahead and check that. We'll do the same thing. We'll apply the transformation to KV, and if we can show that the transformation of KV is the zero vector, then that guarantees that KV is an element of the kernel. Well, since this is a linear transformation, we know that T distributes past scalar multiplication. So this is kt of v. And since t of v, well, what is that? Well, v is an element of the kernel by assumption. So this is k times the 0 vector in w. And we know that any scalar times the 0 vector is just going to be the 0 vector. So that tells us that kv is an element of the kernel of t. Check. And that tells us, so kernel of t is a subspace of v. Check. All right, so that is the first half of the proof that we wanted to show. In other words, what we've just shown is that this idea, the set of all the vectors that are mapped to 0 under your transformation, is a well-defined subspace of your domain. That should pretty much make sense. I mean, if you think about what that's really saying, that's saying if you take two vectors that both are mapped to 0, when you add them, they still get mapped to 0. It's saying if you take a vector that gets mapped to 0 and you multiply it by a scalar, it still gets mapped to 0. That's what it means for the kernel to be a subspace. Now we're going to deal with the range. Now the range is always a little bit harder to work with just because the definition of the range is a little bit confusing. To be in the range, you are a vector of w. Things in w are elements of the range, but to be in the range, you have to have a vector in v that allows you to be mapped to w. So you got to make sure you understand that the range of t, the things in the range of t are vectors in w, but they're the vectors in w such that we know that there's a vector in v that gets mapped to that vector in w. So let's go ahead and see if we can do this. So we're going to sort of separate this because it's going to be a separate proof here. So we need to show that the range of t is a subspace of w. So let's see if we can go ahead and do that. So the first thing we need to do, just like we did up here, is we're going to need to show that it's closed under addition. So let's let w1 and w2 be elements of the range of t. We need to show that w1 plus w2 is an element of the range of t. All right, so let's think about what it means for w1 and w2 to be elements of the range of t. So since w1, w2 are elements of the range of t, this implies that there exists v1 and v2 elements of v such that t of v1 is equal to w1, t of v2 is equal to w2. That's what it means to be in the range. It means that there's things in the domain that actually get mapped to those w1 and w2. All right, but now let's consider what would happen if we applied our transformation to v1 plus v2. So now consider t of v1 plus v2. Since t is a linear transformation, we know that it distributes, so we go over that vector addition, get t of v1 plus t of v2. And t of v1, well, we know that by that, that's w1, and t of v2, that's w2. So what does this tell us? Well, this tells us that t of v1 plus v2 is equal to w1 plus w2. So v1 plus v2 gets mapped to w1 plus w2. Well, that tells us that w1 plus w2 is in the range because we just found something in the domain that gets mapped there. So w1 plus w2 is an element of the range of t. And we showed that sort of in a little bit of almost of a backwards way. We found the thing, right? We actually found the thing in v that gets mapped to that w1 plus w2. All right, let's do the same idea. Let's let w be an element of the range of t. We'll put our check mark back there. And now we need to show that kw is an element of the range of t. I guess we're letting k a scalar. All right, so we need to show that kw is an element of the range of t. Well, again, same idea. We can say that since w is an element of the range of t, that implies there exists a v, an element of v, such that t of v is equal to w. All right, so we know that there's something in v that gets mapped to w. Now, what are we going to get used to get mapped to kw? Well, we should use kv. So let's consider t of kv. Well, we know that the transformation distributes, so we get kt of v, and we know that that's going to be kw. So we just found out that kv will get mapped to kw. So there's this thing back in the domain that gets mapped to this kw. That tells us KW is in the range. So KW is an element of the range of T. Check. And I suppose if we just want to write our little ending here, this means range of T is a subspace of W. All right. So these two things show us that in this definition, this definition is just a definition, but what we just proved is that the sets that I'm defining are not just sets, they're actually nice closed subspaces. The kernel, a subspace of the domain, and the range, a subspace of the codomain. All right, now, before we get into some examples, let's just take a look at a little bit of a visualization to understand what we're sort of talking about here. So I think we'll add in an extra little page here. So we'll just talk about a quick visualization. So visualization of kernel of T and range of T. All right, so the idea here is maybe this big circle here, we're going to let that represent V. And this big circle over here, this is going to represent W. What we're saying, first of all, is let's talk about that kernel concept. What we just figured out is that the kernel of T, which we know is all the things in V that get mapped to the zero vector in W. That's actually a well-defined sort of subspace. So we can actually say that there's a little section in here, its own little space, where all of this stuff, which we would call kernel of T, under this mapping, this entire sort of section gets mapped to the single vector, the zero vector in W. So in other words, our transformation, this sort of black arrow that I'm extending here, this is our transformation. And we're saying that the kernel is this entire sort of subspace of vectors that gets smashed under this transformation into the single zero vector in the codomain. Okay, now let's talk about what the range is. Well, the range, we're saying, is that actually if you take everything in V, everything in your domain, right? So I'm sort of carefully, well, not so carefully, but sort of tracing the entire thing. Then this, under that transformation, is going to be brought in to some subspace of W that we call the range of T. Now, sometimes this range of T will be everything in W. In other words, everything over here gets hit by something over here. But in general, this range of T is only going to be a subspace of W. So even though we know how our transformation works on everything over here, it only hits a portion of our codomain. You'll also notice that in my visualization, my 0W must be inside the range, because we know that there's these things over here that get condensed into that zero vector. So that zero vector is certainly inside the range, which should make sense, because remember, one of the things that must be true of any subspace is that the zero vector must be in there. So of course the zero vector in W is an element of the range of T. We also know that one of the things that's always in the kernel is the zero vector in V. Right? The zero vector in V is one of the things that is always going to be in the kernel. But the idea is that there might be other vectors as well that get mapped to the zero vector in W. So this is basically trying to help you guys understand what we're talking about when we're talking about the kernel and the range. The kernel is everything that is being mapped to the zero vector, and the range is the collection of everything that gets hit at least once under this transformation. All right, let's go ahead and take a look at a quick example before we start to understand the dimension of the kernel and the range. Now, do keep in mind, it is a well-defined concept to say something like the dimension of the kernel and the dimension of the range, because we just proved that they're subspaces. All right, so as a quick example, let's consider this linear transformation. Now, we're not going to prove this is a linear transformation, but you could easily go ahead and do that, right? The linear transformation we're going to talk about is that you're going to take things that are 2 by 2 matrices and map them into R2 by doing this transformation. You're going to apply onto a matrix. The first component of the resulting vector is going to be the trace of the matrix, and the second component is going to be the sum of the matrix. And remember, the sum of the matrix is just summing up all the elements. So we're going to ask ourselves a couple questions here. We're going to try to figure out, is this guy an element of the kernel? Is this guy an element of the kernel? Is this guy an element of the range? Is this guy an element of the range? And then we're going to talk about finding a basis for the kernel and stating the dimension of the kernel. So these first ones are just to get a sense of the idea here. So how do we figure out if something is an element of the kernel? Well, obviously, if we skipped ahead and did E, and we just figured out what the basis for the kernel is, then, well, this guy would be in the kernel if he could be built out of a linear combination of elements of the basis of the kernel. But that's sort of getting ahead of ourselves, so let's just try to do it directly. Let's go ahead for A and actually just apply the transformation. So let's do our transformation of 1, 2, 1, negative 1, and see what we get. So according to this, right, we should do the trace and then the sum. So if we do the trace of this, we would just sum up the diagonal elements. 1 plus negative 1 would be 0. And if we do the sum, we'd get 1, 3, 4, and then back down to 3. So the resulting vector would be 0, 3. Now, 0, 3 is obviously not the 0 vector in R2. So what this would tell us is that 1, 2, 1, negative 1 is not an element of the kernel of T, because even though it gets mapped to the 0 in this component, it does not get mapped to the 0 vector overall. The result of applying our transformation to 1, 2, 1, negative 1 gives us this non-zero vector 0, 3. So this guy is not an element of the kernel of T. All right. Notice we also do get another sort of not necessarily relevant piece of information, but we just learned that 0, 3 is an element of the range of T because we just saw a matrix that gets mapped to it. All right, let's go ahead and check this guy. T of 2, 3, negative 3, negative 2. Well, first thing we would do is take the trace, so we'd add 2 and negative 2, and we would get 0. And then we would do the sum, so we'd add up all the components, 2, 5, back down to 2, to 0. So this guy comes out as 0, 0. That tells us that 2, 3, negative 3, negative 2 is an element of the kernel of T, because this matrix gets mapped to the 0 vector under this transformation. So this guy is an element of the kernel. All right, let's look at some elements of the range. Now, again, working with the range is always a little bit harder because you sort of have to think in reverse. You have to think of, can I find a matrix that gets mapped to 2, 3? So in other words, can we find A, an element of M2 of R, such that T of A is equal to 2, 3? Now, let's just sort of play around with this, right? We need the trace to be 2, and we need the sum to be 3. So let's consider A equals, well, let's make sure our trace is 2. So I guess I could put 1 and 1. Now I need to make sure my sum is 3. So I guess I could put another 1 and then a 0. And if we think about that, if I apply T of that 1, 1, 0, 1, well, the trace, because I sort of set it up that way, would be 2. And the sum would be 1 plus 1 plus 0 plus 1. Yep, that sounds like 3. There we go. Check. So I just found this matrix here that gets mapped to 2, 3. So that tells me 2, 3 is in the range. So 2, 3 is an element of the range of T. Is that the only matrix that gets mapped to 2, 3? Absolutely not, right? I could have done something like this. I could have done 2, 1, 0, 0. Right? That guy would have a trace of 2 and a sum of 3. So there's plenty of choices. All we needed to do was to make sure that there was at least one choice, and that assures us that we know that this element, that this guy, this 2, 3, really is in the range. All right, let's go ahead and look at another one. Right? So for D, we want to know, can we think of something so that minus 1, 0 is the result of the transformation? So again, we got to ask ourselves, can we find A is an element of M2 of R such that T of A is supposed to come out as negative 1, 0. So let's see if we can do that. Let's consider. Well, I want to make sure that my trace comes out as negative 1. So why don't I put negative 1 and then just automatically put a 0. That'll ensure that I can get a trace of -1. Now I need to make sure that my sum is 0, but I don't affect the trace. Obviously, I can put anything I like in these two spots to avoid affecting the trace. So let's just make sure we go ahead and put a 1 here. That'll ensure that the sum is 0, and then we can put a 0 here. So that should be pretty clear that t of -1, 1, 0, 0. Well, the trace is going to be -1. The sum is going to be 0. Check. So that tells us -1, 0 is an element of the range of t. Now, hopefully, you guys have seen after doing these two examples that probably you should be able to do this for any element in R2. So we're actually seeing an example in this very first case where everything in the codomain, everything in R2 is actually in the range. And you guys can sort of confirm that. You can think of anything you like from R2, any random vector, and you should be able to find a matrix such that the trace is the first component of the vector and the sum is the second component. And the reason you should be able to do that is because of the fact that when you have this matrix, you've got 4 different options. You've got 4 different elements you can play around with, but you only have really 2 restrictions. So you should always be able to do it. All right, so now this was just trying to give you guys a sense of how do you figure out if something's in the kernel, how do you figure out if something's in the range. Obviously, in this class, we always like to do things more from a broad perspective. So to wrap this example up, let's actually go ahead and see if we can figure out a basis for the kernel and talk about the dimension of the kernel. In other words, let's not just try to do this for individual things. Let's try to figure out everything that's in that kernel. So let's see if we can do that. So the kernel of t, remember, is every vector in V such that t of V equals 0. All right, so in this case, what that means, what can we say about that? Well, that means if t of A is equal to the trace of A and the sum of A, and that needs to equal the 0 vector. This needs to equal 0, 0, so, or 4, I guess, for A to be an element of the kernel. All right. So let's think about what that means. So that means trace of A needs to equal 0, and sum of A needs to equal 0. All right, let's give ourselves a little bit more space to work with. So we know that the trace of A is supposed to be 0, and we know that the sum of A is supposed to be 0. So let's just let A be sort of a generic matrix, A, B, C, D. What do these two things tell us? Well, these things tell us that A plus D must be 0, and that A plus B plus C plus D must be equal to 0. You can actually think about this as a system of equations. This is really telling us 1A plus 0B plus 0C plus 1D is supposed to be 0, and 1A plus 1B plus 1C plus 1D is supposed to be 0. You could actually rewrite that into sort of an augmented matrix form. It's 1, 0, 0, 1, 0, 1, 1, 1, 1, 0. And we could just do one operation real quick. Let's do row 2 and replace it with row 2 minus row 1. We should get 1, 0, 0, 1, 0, 0, 1, 1, 0, 0. Okay. Now, you guys know how to solve this. This has got rank 2, and it's got 4 variables, so we're going to need 2 free parameters. 2 free parameters, right? Let's avoid parameterizing these guys, right? Avoid parameterizing those lead ones. So let's go ahead and let's let, I guess, C equal to T and D equal to S, right? Because our variables here were A, B, C, D, not X1, X2, X3, XOR, but it would be fine to say that too. Then this equation here would tell us that B plus C equals 0, which implies that B equals negative T. And the top equation here would tell us that A plus D is equal to 0, which implies that A is equal to negative S. So what this would tell us is that the kernel of T would be all the matrices that look like negative S, negative T, T, S. There we go. There's our kernel of t. What does a basis look like for that guy? Well, a basis for kernel of t, remember, if you have the general element, it's very easy to figure out a basis. Take one of the free parameters, let it be 1, and everything else 0, and then reverse. So in this case, let's let s be equal to 1. So we would get minus 1, 0, 0, 1. And then we could also get 0, minus 1, 1, 0. Both of those guys would form a basis for the kernel of t. You could form anything from the kernel by doing s times this guy plus t times this guy. Notice that this then tells us that the dimension of the kernel of t must be equal to 2. So there we go. What we've done is we've actually gone through and found in general that this is what the kernel looks like. Now let's go back real quick and make sure that the things we diagnosed as being elements of the kernel could be built out of things that look like this. So let's just go back real quick. Remember, we found that this guy, 2, 3, negative 3, negative 2, is an element of the kernel. Notice that 2, 3, negative 3, negative 2, well, if we look back at that, this guy here, 2, 3, negative 3, negative 2, right, just as a sort of note here, 2, 3, negative 3, negative 2, right? That's the, sorry, having to just go back and check. Yep, that's what we sort of saw there. This guy is equal to, pretty clearly, negative 2 times this guy and negative 3 times this guy. It'd be negative 2 times negative 1, 0, 0, 1, minus 3 times 0, negative 1, 1, 0, right? Which, of course, it has to be, because what we're saying is that the thing that we found was in the kernel needed to be a linear combination of basis elements. If you go back and check, these guys cannot be used as in a linear combination to form 1, 2, 1, negative 1, which is why this guy was not an element of the kernel. So what we're sort of seeing here is that, yeah, you can diagnose individually very quickly if things are elements of the kernel, but it's also not too bad to actually find out in general what the kernel looks like and be able to talk about its dimension. In our next video, we'll actually state a relation between the dimension of the kernel, the dimension of the range, and the dimension of the domain. And then we'll use that to do a couple more examples, really understanding the kernel and range of different transformations.